So it's my pleasure now to introduce our speaker, Professor Karen Harp. She is a faculty member in of Geology and Peace and Conflict Studies, pretty cool, at Colgate University in the US. Her current research focuses on areas such as the origin and evolution of the Galápagos Islands, deep mantle origins of plumes, plume ridge interactions, analytical geochemistry and trace element analysis, and science education and outreach programs with an emphasis on hands-on experiences, project-based learning, and design thinking. I believe that Karen is joining us remotely, so I will hand it over to her now to be able to start her talk. Welcome, Karen.
Thank you so much. Can everyone hear okay? There's a wicked echo. Okay, well, let's roll with this. Oh, that's much better. Thank you so much. Well, welcome. Aloha, everyone. Welcome, whether you are online or in person. And first, I'd like to congratulate the award winners, of course, and especially Bill White, who was my PhD advisor for the Urey Medal. That's so well-deserved, Bill. Thanks also to the organizers for this rather unexpected invitation, and also for supporting the hybrid version of this conference, which I know is a huge amount of extra work, but it allows many of us to participate who otherwise could not. I will try and make this as close to feeling like I'm in person as I can. I'll do my best with that. So to get started, I need to level with you, though. Never in a million years could I have imagined myself giving a Goldschmidt plenary talk. It's not that I don't have an interesting geochemical story to tell. I think I do, and I assure you, is what we'll do for most of the time that we're here. Instead, it's really an issue of perspective. And let me explain what I mean by that. All of us attending Goldschmidt share a common objective. We want to learn more about how our world works, primarily through the use of geochemical techniques. To do that, we have to engage in two major tasks essential to our work, right? Research and teaching. We perform geochemical research, we educate future geochemists, and we teach others about what we're discovering. But the proportions of our time that we spend on teaching and research, and consequently the strategies we use to approach our research, differ dramatically. And that depends very much on the type of institution where we're based. So here's what I mean by perspective. I suspect, but I cannot prove, that most Goldschmidt plenary speakers probably hail from the left side of this spectrum, from the more research-intensive settings. I come from the opposite side of this spectrum, from a small undergraduate liberal arts college, a perspective heard probably less often in this kind of setting. And all of our research is done in collaboration with undergraduates, not graduate students. So consider this question just for a moment. Were you yourself involved in a research project as an undergraduate? I suspect that many of you were, which illustrates the impact that those undergrad research experiences bring in terms of encouraging young students to pursue careers in the sciences. Those of us on opposite ends of this spectrum have developed by necessity different skill sets to accomplish our research and engage students in that research with us, ones that are appropriate given our operational constraints given to us by the institutions that we're at. So this is what we're going to do today. I'm going to tell you what I think is an interesting and timely geochemical story about mantle plumes for most of our time. And then at the end, we're going to do a short meta-analysis of that project from the perspective of someone at a teaching-intensive institution. And the reason for doing this is that the skills people from each side of that institutional spectrum have developed to accomplish our research are in many cases complementary to each other. And at risk of sounding a bit like an after-school special, I suggest that the intentional collaboration of individuals from across this spectrum is actually really synergistic and will allow us to accomplish even better work than we already do toward our collective goal of understanding our world through geochemistry. So let's get going on the story. As summarized by Bill White yesterday in his Urey Medal talk, there's been almost a paradigm shift in what we know about mantle plumes over the past decades, owing in no small part to the integration of advances in the geochemical, geophysical, and geodynamic studies of ocean islands. What we're going to do is we're going to trace that arc, that evolutionary arc of changes in mantle plume models by considering a case study of the Galápagos mantle plume. The Galápagos Islands are located about 1,000 kilometers off the west coast of South America, and of course they're made famous For their unique flora and fauna, having been the source of inspiration for Darwin's groundbreaking work on natural selection and evolution. Darwin also was a really good geologist, and he made some spectacular observations and important interpretations while he was on his voyage and in the Galapagos, which really illuminates the fact that these islands host not just important biological questions, but also geological ones. The Galapagos volcanoes, of course, are the product of the Galapagos Mantle plume, which sits approximately here in red on the western edge of the archipelago. The plume is beneath the Nazca Plate, which is moving almost directly to the east at about 50 kilometers per million years. The islands are 100 to 200 kilometers south of the Galapagos spreading center, which is an intermediate rate spreading ridge that separates the Nazca Plate from the Cocos Plate to the north. And the ridge has a complex history of interactions with the plume. It's a complicated relationship because the ridge is migrating northeast relative to the plume. So between 5 and 8 million years ago, the ridge sat on top of the plume, just like the Mid-Atlantic ridge sits over the Icelandic plume today. Consistent with our original model for mantle plumes, current volcanic activity in the Galapagos is concentrated in the western archipelago, where there's an eruption from one of the young shield volcanoes there every few years, like this one you can see from the 2005 Sierra Negra eruption. The primary geochemical tool that we're going to use in this story is radiogenic isotope ratios. And I imagine that most people in the audience are intimately familiar with these concepts. But since this is a plenary, I'd like to take about a minute and clarify some terms so that we can all be on the same page conceptually. So if you're an isotope geochemist, like check your email for a second, and then you can join us again. So as we all know, over the course of Earth's history, the planet's developed different major reservoirs: the crust, the upper mantle, the core. Each of these formed through different thermal processes during which elements with distinct properties fractionated from each other, right? We all know this from intro geochem. Because the isotopic systems we're using have long half-lives, the ones listed up here, on the order of hundreds of millions to billions of years, over the course of Earth's history, these reservoirs have developed distinctive isotopic signatures that reflect those integrated thermal histories. So for instance, having a melt removed from a material like the mantle early in Earth's history causes large ion lithophile elements, incompatible elements, to be extracted from that material, ultimately leaving the residual to have a depleted isotopic signature like the upper mantle. The melt, in turn, is rich in those incompatible elements, and so over time developed what we cleverly call an enriched signature, like continental material. Generally, mantle plumes, for the most part, are thought to be supplied by lower mantle material that has had some enriched surface material recycled into it via subduction, so they are enriched relative to the depleted mantle, but depleted relative to the continental crust. Basically, the bottom line is that I'm going to use these terms kind of loosely today as a relative scale, not super precisely. So let's get back to the Galapagos. The geochemical story about the Galapagos began in the late 1970s when Bill White and Al Hoffman reported some of the first isotopic measurements from the Galapagos Islands. Not surprisingly, they detected enriched plume-like compositions in the west, as we expected from plumes, given what we knew at the time. But in the east, they measured compositions that were strikingly depleted, barely distinguishable from depleted morb, which was really an unexpected discovery. And at the time, they attributed the depleted signatures to incorporation of the asthenosphere into the plume, but they weren't really specific about their vision for the plume model itself. This pattern was confirmed by Geist et al. In 1988, who added more subaerial samples to the first study and concluded that this geochemical pattern has persisted throughout the history of the present-day Galapagos Islands, which they determined by backtracking dated lavas to their points of eruption over the plume center in the west. They proposed a plume model in which the depleted upper mantle was being entrained into a torus or a donut shape within the plume stem. And on the basis of this model, they predicted that there should be more enriched lavas in the submarine material erupted east of the main archipelago up here, if we could actually sample those submarine lavas. White et al. In 93 added more geochemical and geochronological analyses of subaerial samples, confirming the horseshoe pattern with the new data, sort of became known as the horseshoe pattern in general. And they took a different approach to the plume model, and they based it instead on analog experiments by Richards and Griffiths. and suggested that the plume was being bent eastward by the currents in the upper mantle generated by the motion of the overlying Nazca plate. And as the plume bends toward the east, thermally buoyant depleted upper mantle heated by that plume rises into the bent part of the plume, which becomes progressively diluted by depleted mantle toward the east, explaining the strongly depleted compositions in that part of the archipelago. A research cruise around the archipelago collected submarine lava samples, shown here as yellow circles, increasing the sample density from both the area between the ridge and the plume, as well as in the east and the northeast. No enriched lavas were found in the northeast, and so we went with the bent plume model that was proposed by Bill and his co-workers in the previous paper, and we added a bunch of colors to the model. So that was about it there. Sadly, though, the bent plume model met its demise in a tomographic study out of the University of Oregon, which showed that the seismically imaged plume sure does not look like it bends to the east. Instead, it takes a bit of an excursion northward at about 80 to 100 kilometers depth toward the Galapagos spreading center, and then it bends back towards the plume conduit, but all in the western Galapagos. At about the same time, an important story was emerging from Hawaii. As you know, Hawaii has two distinct chains of volcanoes, the southern Loa Trend and the northern Kea Trend. A series of isotopic studies that employed high precision isotopic ratio measurements led to the realization that the shield phases of Hawaiian volcanoes in each chain are also isotopically distinct from each other, expressed most strongly in lead isotope ratios, but also apparent in other isotopic systems. The southern Loa chain is more enriched in terms of its isotopic signatures, whereas the northern Kea chain erupts more depleted lavas. By depleted here, we mean just more depleted than the Loa Trend, not as depleted as those in the Galapagos in the east. This pattern's become known as bilateral compositional asymmetry, and it inspired a variety of different models for a compositionally heterogeneous Hawaiian plume, from concentric to plum pudding configurations. Weiss et al. In 2011 proposed an important idea at this point, which involved consideration of the isotopic data in the context of geophysical studies of the Pacific Mantle. Seismologists have identified regions along the core mantle boundary characterized by low seismic shear wave velocities, as you know, known as LLSVPs, or large low shear velocity provinces. The LLSVPs are interpreted as thermochemical piles of denser and probably hotter material than the surrounding lower mantle. But the important observation here is that Hawaii sits at the northern boundary of the LLSVP. Weiss and co-workers proposed that the compositionally distinct filaments ascending from the deep mantle to feed the plume came from two sources. One was the enriched material coming from the LLSVP, and the more depleted Kea material coming from the ambient lower mantle, and they were joining together and expressing themselves at the surface, feeding the Loa chain and the Kea chain. A series of modeling studies by Cinzia Farnatani and Al Hoffman and others determined that strands of geochemically distinct material could actually maintain their integrity all the way from the deep mantle to the surface with minimal mixing, so that their distinct compositions would then supply each of the Hawaiian chains. Soon after publication of this idea, several additional plumes were located at or near LLSVP boundaries, and were determined to have similar bilateral compositional asymmetry consistent with this idea. That includes the Marquesas, Society Islands, Easter, and Tristan in the Atlantic. According to most seismic studies, the Galapagos plume also sits on the northern boundary of the Pacific LLSVP, just a little farther east, or a lot farther east. So we figured it was worth a look to see if that bilateral asymmetry model might apply to the Galapagos plume as well, despite there being many striking differences between the island chains. The two most glaring being the lack of two parallel volcanic chains in the Galapagos and that isotopic pattern of the horseshoe with strongly depleted signatures in the east. The asymmetric plume model for Hawaii is informed primarily by high-precision radiogenic isotope data, with an emphasis on lead isotopic analyses, as I said before, but done with rigorous leaching methods to get rid of any influence or contamination from seawater and other sources. The data in Weiss's 2011 paper were measured at the University of British Columbia under her guidance in her lab using these methods. Existing isotope data from the Galapagos at the time, however, varied fairly significantly in its precision. It was been collected gradually over a few decades, was generated in many different labs, and it was exposed to many different leaching protocols. So it was pretty challenging to carry out a proper comparative study. So we prepared a set of more than 80 samples from across the Galapagos. You can see the regions broadly indicated here. That represented the isotopic variations in the island chain, all of which had been well characterized for their major and trace element contents. These were analyzed for lead, strontium, neodymium, and hafnium isotope ratios at the University of British Columbia using the same methods that Weiss and her group employed to build their Hawaiian data set so that we could make a fair comparison between the two systems. Let's jump straight to the results. Regardless of which isotopic system you examine, it turns out that there are two quite well-defined compositional groups in the Galapagos, one more enriched, one more depleted. In other words, it is bilaterally asymmetric. There's a more enriched group in the south and the west, and there's a more depleted group in the north and the east. They don't define two parallel chains like in Hawaii, but are geographically divided by the yellow line that you see in the map on the right here. So it's two zones. This pattern of a more enriched and a more depleted zone persists regardless of which isotopic systems you consider. So I'm not going to show you like an entire series of binary isotope plots. And instead, we're going to shift into a different way of thinking about this. Rather than belabor it, we're going to treat this like a thought experiment. We're going to propose that both the Galápagos and the Hawaiian plumes originate at the boundary of the LLSVP, with their plumes supplied by material from the two lower mantle reservoirs, the LLSVP and the ambient mantle. That's our thought experiment, is to accept that premise. A few interesting implications emerge from this idea. The first is that if the north side of both plumes is supplied by the lower mantle, Hawaii and the Galapagos should share a common mantle source, and that source should look like lower mantle compositionally. Sounds fairly obvious. Let's look at lead space for this example. Lead 206, 204 on the x-axis, 208, 204 on the y-axis. The yellow field here is the Galapagos. The green is Hawaii in terms of the circles, not the colors within them. Indeed, in any of the isotopic spaces, not just this one, of course, Galapagos and Hawaii do share a common composition, one that is intermediate in terms of its enrichment, consistent with what we expect for the lower mantle. Now, this isn't exactly news, right? Hainan and Graham in 1996, and before that, Hart and co-workers identified a common component in many ocean island arrays, which are shown here from Bill's textbook, centrally located in isotopic space. For those in the audience unfamiliar with this figure, it represents three-dimensional isotopic space in terms of strontium, neodymium, and lead ratios. The four corners of this tetrahedron are defined by compositionally distinct mantle reservoirs, or genera, in the parlance of Bill's talk yesterday, signatures of which have been detected in ocean islands from around the world and which are being sampled to varying extents by those plumes. So EM1 and EM2 are some form of enriched material that originated at Earth's surface, such as recycled subducted pelagic sediments for EM1, or materials that were once present on continents for EM2. The most commonly invoked source for the high mu end member in the bottom right corner is ancient subducted oceanic crust, which is dehydrated during subduction and then stored in the mantle for 1.5 to 2 billion years prior to incorporation into mantle plumes. DMM is simply the depleted upper mantle, which we've mentioned before. The area indicated as FOZO in this diagram defines an intermediate compositional range consistent with what we expect for the ambient lower mantle. There are some complex issues in terms of what to call this central reservoir, so we're not going to deconstruct that today. This is a topic Val Finlayson raised in her talk yesterday, for instance. For now, we will do as Bill also did in his talk and call this moderate isotopic composition prima for prevalent mantle, and note that it represents isotopic signatures expected for the lower mantle. So what we need to get out of this story, or this particular diagram, is that many mantle plumes around the world are sampling the central reservoir that has intermediate isotopic signatures, which we are attributing to the ambient lower mantle, just like we're seeing in Hawaii and the Galapagos. The second concept to emerge from our thought experiment is that if the southern enriched zones of both Hawaii and the Galapagos are sourced by the LLSVP, that means we have an opportunity to learn something about the compositional structure of the LLSVP. Let's look at neodymium lead ratios here, neodymium on the x-axis, lead on the y-axis. But again, this applies in any isotope ratio space. Here are the Hawaiian and Galapagos fields, Galapagos in the yellow field and Hawaii with the green circle around them. And let's add the mantle end members we just discussed, as well as mixing lines between them. We see the intersection of both plumes with the prevalent mantle at the center of the array. And then we see that the Galapagos and Hawaiian arrays are mixing with different mantle reservoirs. Hawaii is mostly trending towards the EM1 mantle end member, potentially recycled oceanic sediment. And in contrast, the enriched lavas from the Galapagos are trending towards high mu, the reservoir attributed that originate as ancient subducted oceanic crust. And I just said that, so there you go. You can see it animated there. This supports previous proposals that there's a lot of ancient recycled material in the LLSVPs, but what is most important here is that it provides additional insight into the fact that it's different flavors of ancient recycled surface material, and that they're located in different parts of the LLSVP. But if we explore our thought experiment a little further, things get a bit more complex. If, as we're proposing, the Galapagos and Hawaiian plumes are formed by the same mechanism, that's our thought experiment, rising from the core mantle boundary at the interface of the LLSVP and the ambient mantle, we also need to explain some of the major differences between the two systems. For starters, where are the compositionally distinct chains of volcanoes in the Galapagos that we see so nicely laid out in Hawaii? We think this is mostly just an issue of geometry. In Hawaii, the edge of the LLSVP has been mapped to run northwest-southeast, fundamentally parallel to the Pacific plate motion direction today. Any volcano formed in the Loa zone will be supplied by the LLSVP, and it will continue to be supplied by the LLSVP during its lifetime. Volcanoes that replace it along the chain will also be supplied by the LLSVP. Similarly, the same thing's going to happen for the Kea chain volcanoes, continuously being supplied by the lower mantle source. I'll give you a very low-tech illustration of what I'm trying to convey here. So if you can see me in the corner here, let me move this screen. This is our plate. In this case, it's the Pacific plate. Here we have our compositionally distinct chains or filaments within the mantle plume, the Hawaiian plume in this case. So if we think about the boundary between those two filaments in the plume, being the strike of it being this way, and we make that parallel to the direction of plate motion, and the plate moves, you'll see that we end up with two parallel chains. It's not really rocket science, it's just a proposal of geometry. Okay, let's turn to the Galapagos. In the Galapagos, the LLSVP boundary also trends northwest-southeast, but Nazca plate motion is to the east. It's oblique to the LLSVP boundary. Any volcano initially formed in the Western archipelago is supplied by the LLSVP source initially. But as it's carried away by the Nazca plate to the east, the volcano will cross the LLSVP boundary. And once east of that, presumably, its source will shift to the lower mantle. That means that late erupted lavas will have more depleted signatures than initially erupted lavas, and the earlier enriched lavas will be covered or buried by the younger, more depleted lavas. It means that the compositional stripes are basically being erased because of that oblique orientation of the boundary of the LLSVP relative to plate motion. And so if we go back to our striped plume, remember this is Hawaii, and instead of having motion of the plate be parallel to the strike of the boundary of the LLSVP, we're going to turn our plate motion to have a different orientation. And what we're going to end up with here is basically no way to see the two stripes in a really nice, organized, clean, separate way. So it's a simple issue of geometry we'd like to propose. Yesterday, Nicole Williamson invoked the same concept to explain the geographic distribution of isotopic systems at one Hawaiian island, Kauai, and which was in place when the Pacific plate motion was slightly oblique to the LLSVP boundary. So the source of depleted material in the Galapagos and Hawaiian plumes is a long-standing question, especially the most depleted signatures in the Galapagos. Is the depleted material an intrinsic component of the plumes, or is it the result of entrainment of depleted upper mantle? So to get at this question, we applied the method designed by Fitton et al. In '97 for studying the Iceland plume. They defined delta niobium as a reference line in niobium yttrium and zirconium yttrium space. That's along the x-axis. And they use it as a discriminator for mantle source based on how mid-ocean ridge or mid-Atlantic ridge compositions differed from those of the Iceland plume. Lavas with a positive delta niobium are attributed to deep mantle plume sources intrinsic to the plume, and they define the OIB field, basically shown in purple here. That represents the lower mantle. A delta niobium that is negative is characteristic of material sourced in the depleted upper mantle, the Morb field, shown here in green. And when we plot the full Galapagos data set on top of this discrimination diagram, no samples fall in the plume-hosted depleted source quadrant. All the depleted Galapagos material is limited to the upper mantle Morb source quadrant. So we concluded that the most depleted signatures from the Galapagos reflect contributions from a depleted upper mantle source, and that Galapagos lavas define a mixing trend between the depleted Morb source and the complex enriched plume. Hawaii and some other plumes are believed to have depleted components to them that are intrinsic to those plumes. Hoffman and Farnatani, for instance, proposed that the depleted material being melted to generate rejuvenated Hawaiian lavas originates in the plume from its cooler margins. So why would this be lacking in the Galapagos? Well, there's a few potential explanations for that lack of an intrinsic depleted component in the Galapagos. The first and simplest is that there isn't one. It's not an especially satisfying explanation. It's pretty tough to prove, but at least it could potentially provide some insight into the lower mantle plume source composition or structure, but we can't really do too much with that one. Plus, in their geochemical study from 2016 of the ancient track of the Galapagos plume, specifically of Paleocene seamounts about 62 million years old that were accreted in Costa Rica, shown here in the red square, Bukes et al. Identified lavas with depleted isotopic and trace element signatures comparable to those from the Northeast Galapagos. And on the basis of their field evidence, they proposed that these lavas originated as seamounts produced by the Galapagos plume, far from any potential interaction with the spreading center, and therefore concluded that these depleted signatures represent evidence of depleted material intrinsic to the ancient Galapagos plume. If there is a depleted component in the plume, then why aren't we detecting it in the present day Galapagos? One scenario is that the depleted component is not melting today, and it hasn't melted in the past 3 to 4 million years, the time frame of the current islands. The Hawaiian plume has a higher flux and a higher potential temperature than the Galapagos plume, and perhaps the Hawaiian plume therefore permits melting of the depleted lower mantle component that may not be possible at smaller, cooler plumes like the Galapagos. Bukes et al. Suggested that the depleted material intrinsic to the Galapagos plume that they did detect in those seamounts from 62 million years ago only melted because the plume was hotter at that stage than it is today, and since then it has cooled down. Another option is related to the current tectonic setting of the Galapagos. It's well established that many near-ridge plume systems experience extensive mixing with depleted Morb mantle, including the Cretaceous Hawaiian plume, and just as we showed, the present-day Galapagos. Any small volume of depleted lower mantle material intrinsic to the plume may simply be overwhelmed by higher volume contributions from entrained upper mantle owing to its near ridge setting. And the important point here is that, as was the case with the compositional stripes, how the compositional structure of a mantle plume is expressed at the surface is strongly affected by the conditions it encounters near and in the lithosphere. So what can we get out of this project? Despite having radically different characteristics from each other, the Galapagos and Hawaiian plumes may have the same origin mechanism supplied by parallel filaments from the LLSVP and the lower mantle. And if we accept that premise, then our findings suggest that the Pacific LLSVP is heterogeneous, and it consists of multiple flavors of ancient recycled material spatially distributed in a clear way. But the critical message here from a bigger picture perspective is that despite common origin mechanisms, the surface expression of plumes can look very, very different from what it looks like at depth, depending on the tectonic setting where the plume meets the surface. In Hawaii, where there are no nearby plate boundaries today, and the LLSVP compositional boundary is parallel to plate motion, we may have the most pristine or unfettered view of a mantle plume and its closest relationship to what it looks like at depth. By contrast, in the Galapagos, several factors conspire to make it more challenging to decipher the plume's lower mantle compositional structure, including the adjacent mid-ocean ridge that causes entrainment of depleted upper mantle into the plume, and of course, the orientation of the LLSVP compositional boundary oblique to plate motion. Several even bigger picture implications emerge from this study as well. If even a fraction of major plumes are generated from the edges of LLSVPs, then we have a really important tool. It's invaluable for studying the lower mantle's compositional structure on a global scale. Furthermore, though, if we're going to use mantle plumes to understand the compositional structure of the lower mantle, as I suggest this tool could be used to do, and many others have as well, of course, earlier, we have to consider, though, that the superficial expression of the plumes may not directly reflect the lower mantle structure, but that it can be radically affected by the tectonic setting where the plume meets the plate. And we're going to have to deconstruct that in order to see deep into the mantle. So by capitalizing on regional studies of ocean island systems, we're going to have to disentangle the influence of tectonic setting from the plume structure and begin to learn more about mantle in order to begin to learn more about mantle plumes and the evolution of the lower mantle. Furthermore, the confluence of advances in geophysics and geochemistry makes studying mantle plumes right now especially important. Over the past decade, seismologists have documented more plumes that originate at the core mantle boundary, illuminating their relationship to LLSVPs in ever-increasing detail. These bodies may be repositories of ancient subducted crust, but they may also preserve remnants of primordial material that holds clues about early Earth. Seismology's also identified increasing numbers of ultra-low velocity zones and mega ultra-low velocity zones along the core mantle boundary, often associated with major plumes like Hawaii or the Galápagos, as was articulated by Lee and coworkers yesterday. These regions may record information about early Earth differentiation, core mantle, chemical reactions, even the collision of Theia with Earth to form the moon. So documenting their composition and distribution is an important task using this tool. At the same time, we're experiencing both improvements in the precision of existing radiogenic isotope analyses in terms of methods, as well as the development of new isotopic methods with properties appropriate for examining not just the long-term evolution of Earth's mantle, but the interaction of the mantle with the core and insights into early Earth's evolution, as was raised several times, for instance, by Val Finlayson and Brad Peters in their talks yesterday as well. And that's what I meant to show you earlier as well. So this is an example of some of those systems that are coming to light or coming online or already online to help us understand more about these major reservoirs along the core mantle boundary. Okay, so before we close, let's contemplate that meta-analysis of this project as I promised. Our goal here, remember, is to deconstruct the story I just told from the perspective of someone at a primarily undergraduate institution to understand our strategy for tackling research questions. And to be crystal clear, none of this is being stated with any negativity. Virtually everybody I know in a similar position to mine is in it because we love it and we wouldn't do anything else. We just have different operational boundary conditions than major research institutions. Okay, so first some context to frame this discussion. Colgate University is a small liberal arts college in the heart of upstate New York with about 3,000 undergraduates. So that means we do all of our research with undergrads rather than grad students. And to integrate undergraduates fully into our research, it takes some strategic thought, given the differences they present from grad students, the biggest limitation being the time you get to work with them. Normally, we get the full, near full attention of an undergrad research student for about 10 weeks during the summer. Usually they continue to work on the project for another semester or two as they complete their senior theses, but the time you get then is shared with their other courses and all the 6,000 other things that they're doing these days, which is a lot, believe me. If you're really lucky though, maybe you get them for a second summer, but that's it. Ideally, from an educational perspective, our research students should have a well-crafted intellectual experience consisting of a research story with a compelling question and an investigative middle and a conclusion, and if possible, some field experience. They can't just be generating data without thinking about it. The questions need to be accessible in terms of required depth of knowledge, meaning that the intellectual on-ramp has to be relatively short, because these students are so early in their geoscience careers, they don't have depth of background. But the questions also have to be substantial enough to lead to senior theses at the minimum, and ideally to a story they can present at conferences such as AGU or GSA or this one. So given these requirements, the students' research projects need to be carefully designed, tractable, and self-contained. What we have to do then is design our bigger picture research questions so that they can be addressed incrementally through the synthesis of these many smaller projects. The students also need to be able to acquire data relatively quickly. I operate an elemental analysis lab with a workhorse quadrupole ICP-MS, which does a fine job generating trace element data in rock samples. We also have an XRF for major element analysis. It's on its way out. So we have been in a privileged position for an undergrad institution resource-wise. This equipment permits our students to do major and trace element analysis on samples, as well as petrographic work and field work, but we do not have the capacity to do much more sophisticated geochemical analysis in-house. In terms of publications, realistically, it's only the rarest of students who manages to author a publishable paper while they are an undergrad. Instead, we write the papers, and they are syntheses of several years' worth of projects usually, and they have student co-authors, and they get published well after the students have graduated. So let's consider the Mantle Plume story I just told. This story didn't start out to contemplate the origins of mantle plumes. Instead, it was built from bite-sized pieces. See, get it? Involving less expansive questions with a more regional focus. Here are the locations of those regional studies we carried out in the Galápagos. They were supported by a series of NSF grants. And the questions have ranged from the origins of the many seamounts in the northern Galápagos region to why Floriana's geochemical signature differs from the rest of the islands, or how a single Galápagos volcano evolves over time. These investigations, in turn, are built from multiple smaller research projects. Each diamond on the map represents a student who has collaborated on one of these projects over the years, which comes to a total of 39 whose data or work in some way are incorporated into the story I just told. Let's look at how this sits in terms of moving forward. Here are the students, here are the various regional projects that constitute the component parts of the story I just told. And over time, this strategy ends up building two key resources. The first is a significant data set of major and trace element data from across the archipelago. And the second is a repository of well-characterized samples whose geologic settings are thoroughly documented. These resources lay the groundwork for thinking about broader questions that reach beyond the regional studies, ones that require more sophisticated analytical methods, such as geochronology or isotopic analysis, like the one we just discussed. So we use what we've learned from the regional studies to build the case to request funding to pursue those analyses and to establish collaborations with more specialized research labs. So these collaborations with the other end of that institutional spectrum I mentioned at the beginning bring with them many potential benefits. First, the opportunity to forge relationships with PIs who look at broader questions, and that brings new perspectives to what we're looking at, and everyone learns a lot in that process. Our undergraduates, maybe they get the chance to visit that institution, to use instrumentation they couldn't otherwise, or work with some of the people involved at that research institution. Maybe they get a glimpse of what grad studies might be like. And importantly, they realize that many other people are interested in their work, not just me or the small number of us back in their group at home, which is often a really effective motivator for them to pursue careers in geoscience. Maybe grad students get involved in the project and they take on mentoring roles with those undergrads, which often inspires them to pursue careers that incorporate some kind of a STEM education component. Sometimes these collaborations inspire additional projects, like a review paper I've been engaged in over the past few months with a group of fabulously talented women from across the institutional spectrum, so keep an eye open for that. And some projects can even result in new ideas for teaching geochemistry and science education in general, too. I'll give you two examples of that. For instance, one of the challenges we face at small undergrad institutions and small grad institutions is that our students only have us to engage with about our specific discipline, and they really need and flourish when they have the opportunity to hear more opinions and engage in dialogue with others. So in 2017, well before the pandemic, when we all went online, we initiated a course that invited people studying mantle plumes to give video-based seminars tailored explicitly for upper-level undergraduate and early graduate students about their research. The recordings of these presentations have been compiled into a website. You can see the link here. It's available to anyone who wants to give their students access to recent developments in mantle plume studies. You can see the cavalcade of mantle plume stars listed here who've generously contributed their time to this project, and these connections all grew out of collaborations with them in other kinds of projects for the most part. If anyone has a presentation they'd like to have included in this resource, I would love to host it. So please do not hesitate to get in touch with me if that's the case. Another example of an educational project that's grown out of these kinds of collaborations is the Virtual Galapagos, as we call it, a project in its early stages to build an interactive website to teach middle school children about science through the interdisciplinary lens of the Galapagos. Because the content is all designed and implemented by undergraduate STEM teachers in training, they in turn get experience designing interactive, interdisciplinary, collaborative science curricula, and they get in turn to collaborate with the network of scientists and naturalists who work in the Galapagos. So we're hoping that this is going to make a difference in the long run, and it brings a lot of people together in the process. Ultimately, these efforts also contribute to the front end of the pipeline that encourages students to pursue careers in the geosciences and in STEM education. Of the 39 students who have somehow contributed to this project, here is the breakdown of their current activities. These are the ones that did not pursue careers in the geosciences. You cannot win them all. Maybe someday the 6 in business will be able to donate some money to the projects. But of the 39, 20 of them have pursued careers in the geosciences. And of those 20, you can see their whereabouts and what they're up to broken down as follows. And notice how many of them have pursued or are pursuing careers similar to ours. There's 13 of the 20, just as a reflection of what I asked you at the start of this talk about whether you were involved in research as an undergraduate. It really does have a major impact on the career choices of many students and constitutes a critical piece of our pipeline into our field. So having considered how this project was accomplished at this granular level, I hope to leave you with a few final thoughts. To understand some of the most pressing research questions in our field, we need to consider a range of spatial scales from the regional to the global. They inform each other, and bringing researchers together who work on global questions with those who know regional geology will only enhance our ability to understand Earth systems. This first goal is facilitated by collaboration across the institutional spectrum. People from different institutional settings bring different knowledge, skills, and perspectives to the table that are complementary for achieving our collective research goals. And finally, to optimize the impact of recent advances in geochemistry and geophysics, it's essential that we collaborate across our geoscience disciplines to take our understanding of mantle plumes, Earth's interior, and even the formation of our planet to an entirely new level. And we're hearing that throughout this conference already. I need to acknowledge all of the students who have been involved in these projects over the years, as well as the institutions that have supported our efforts. And before I close, I'd like to echo what was said at the beginning of the session and take another moment on behalf of our community to acknowledge the sudden and tragic loss of one of our favorite isotope geochemists, Jasper Conter. He was an important contributor to the field of isotope geochemistry and a real innovative thinker, known especially for his ongoing work understanding the Samoan plume. Many of us here at Goldschmidt and in the greater geoscience community considered him not just an invaluable colleague, but also a great friend and one of the nicest people you'd have the honor of working with or knowing. Our thoughts are with him and his family and friends at this challenging time. And with that, I will close. Thank you so much. Enjoy the rest of your conference, and aloha. And I'm happy to take any questions if we have them, but I can't really tell what's going on at the moment. They're muted.
Are we still muted?
No, you're not.
Karen, are we still muted?
No, you are not. I can't.
Oh, perfect.
It's like I ended with complete silence, and I was like, oh my God. The apocalypse has come. Anyway, I'm happy to take questions if anyone has them.
Yep, so we are happy to take questions, of course. If you're here in the room and you have questions, please come up to the mic, and then we'll also be monitoring the Q&A of the Zoom. If you're online and you want to drop questions in there, we'll be sure to catch them. Yes, please.
Hi, Karen. This is Molly Anderson. Great talk.
Hi, how are
Thank
you?
Good. How are you?
Good, thank you.
I was just curious if you could elaborate why the EM1 and high mu components would be systematically distributed in the LLSVP the way that this sort of implies, because we presumably these are going down together when we recycle crust, right? So what do you think is happening there?
Honestly, I don't know is the honest answer. I know that there's a lot of debate, or there's some debate at least, about how this would work. Your question makes perfect sense. How they would end up distributed, I don't know. We know they are, right? Because we have different mantle plume systems that are tapping just EM1 or just EM2 or just high mu. So that must be happening. How that happens or how it gets sorted out, I don't know. And I know like Aaron Petrushka had a really interesting paper in 2012 where he talked about maybe we can't, he was basically trying to identify those subsets within just the Kilauea system, if I remember it correctly, and pointed out that this is a
Ooh.
Oh.
All right, sorry about that, but we want to thank you again for joining us. And of course, we'll make sure that we give her another round of applause and thanks to Karen. Enjoy the rest of your conference.